So let's state some general properties of determinants. The first important property that we'll point out is that, in general, taking determinants is quite difficult, but sometimes it's not. And one class of matrices for which determinants are not difficult to calculate are triangular matrices. There's a theorem that says the determinant of a triangular matrix is just the product of its diagonal entries. So here I have a 4x4 matrix, and again, typically a 4x4 determinant is very difficult. But this matrix is upper triangular. So this theorem says this determinant is not very difficult. So think about why this theorem is true. Well, if I were doing this, I would probably just take a column 1 expansion because there's 3 zeros, and then I have this 2. So the 2 pops out, and then I delete that row in that column, and now I have a 3x3 matrix to take a determinant of. Well, here I'm just going to do a column 1 expansion again. So my -1 will pop out. I delete that row in that column, and I'm left with another determinant calculation. But here I'll choose a column 1 expansion again, so the 10 pops out, and then I'm just left with the -9/5 here. So for this 4x4, when I do all these column 1 expansions, I just end up multiplying all of the diagonal entries together, and in this case I get 36. So generally determinants are hard, but for triangular matrices, we just multiply the diagonal elements together to get the determinant. Determinants also play nicely with some of our algebraic constructions. If you think about how these column and row expansions work, since choosing columns and rows doesn't matter in our determinant expansions, remember that the columns of A are the rows of A transpose. So a column 1 expansion of A is actually the same thing as a row 1 expansion of A transpose. For this reason, I like to think of this as saying that determinants are sort of insensitive to transposition. So if we take the determinant of A transpose, that's always the same thing as the determinant of A. It also turns out, for more complicated reasons, that determinants respect products. So the determinant of the product of two matrices is always the product of the two determinants. So let's see an example of this. So here I have a matrix factorization. On the left, I have some 4x4 matrix, and I've managed to somehow factor this matrix as the product of these two other matrices. The first thing I want to point out is on the right here, my first matrix is upper triangular, and so that determinant is actually very easy. It's just the product of the diagonal entries. 1 times -3 times 2 times 1 is -6. And this matrix on the right here is lower triangular, so its determinant is easy. I just, again, multiply the diagonal entries together. -1 times -1 times 2 times 1 equals 2. Well, so here, since I can calculate these easier determinants on the right, my product rule tells me how to calculate the determinant of the matrix on the left. This complicated matrix is the product of these two simpler matrices, so the determinant of this complicated matrix is the product of the determinants of the simpler matrices. In this case, we get -6 times 2 is -12. So once again, we see this situation where we can take something complicated and break it down into easier parts. So let's see.